Astrophysics, the study of our universe, can feel detached from our lives here on Earth, but it doesn't need to be. Here in Potsdam, we've recently hosted a large conference with researchers from around the globe. In the process, we've asked some experts to break down key astrophysical concepts, from galaxies to cosmology. In this last episode, we'll meet Dr. Federico Lelli and Elena Asensio. They'll introduce MOND, an alternative theory of gravity that doesn't require dark matter.
I'm Federico Lelli. I am a researcher at the Arcetri Astrophysical Observatory in Italy, and I work mostly on galaxy dynamics, both nearby galaxies in the local universe as well as galaxies in the high redshift universe. So MOND stands for Modified Newtonian Dynamics, or Milgromian dynamics, to honor the person that proposed this theory, which is Moti Milgrom. MOND is essentially an alternative to particle dark matter. So instead of adding invisible particles in galaxies and in the universe, the theory posits that the dynamics does not work as we expect in a Newtonian context or in a general relativistic context, but needs to be modified in the appropriate regime. And the regime in which MOND kicks in, and so where the modification occurs, is a regime of extremely low accelerations. And in fact, one of the key ingredients in the theory is a so-called acceleration scale called A0, which is essentially a constant, a number, that tells us when it may be appropriate to keep using the common law from Newton and Einstein, and whether instead we should move to the new dynamical theory. I mostly work on the internal dynamics of galaxies, which essentially consist in tracing the motions of gas and stars inside galaxies. And these motions is dictated by the mass of the galaxy. So in the standard dark matter context, in order to explain these motions, we need to add a so-called dark matter halo, which is essentially a halo of invisible particles that is supposed to surround galaxies. Whereas in the MOND context, what we need to do is to take the observed mass that we see in stars and gas and use the MOND equation rather than the Newtonian equation in order to explain the motion of the actual particles, so stars and gas. So my research is quite closely related to this, because by observing the eternal motion of galaxies, we can test at the same time both the standard context with dark matter as well as this alternative theory called MOND. MOND was proposed by Moti Milgrom in 1983, so it's exactly 40 years ago. So it's not a new theory. It has been proposed and further developed for now quite some time. And at the time, let's say at the beginning of the 80s, it became quite clear that the so-called rotation curves of spiral galaxies become flat at large radii. So to give some context, when we look in our solar system, planets that are farther away from the sun, they rotate slower than planets that are in the inner parts of the solar system, and that's essentially because the gravitational force from the sun is less strong as we move towards larger radii. So this is generally called the Keplerian decline, in the sense that the rotation velocity of the planets declines as one moves from small distances to the sun farther out. So one may have expected that the same occurs in galaxies, that the galaxy rotates faster in the central parts where there is the bulk of the visible mass, and then as we move to the other regions, the stars and gas would start to rotate slower because there is less gravitational attraction. But instead, what we have observed now for many years, starting from the 70s and 80s, is that essentially all the galaxies that we observe tend to give a relatively flat rotation curve in the inner parts, which means that the rotation velocity does not decline with radius, but actually stay constant. And in the standard context, this is indeed interpreted by adding a dark matter halo, but one of the features that is striking is that the velocity is constant, right? It's not increasing or decreasing or wobbling around, but seems really to reach a constant value as one increase with radius. And so this is a sort of regularity in the problem of the dynamics of galaxy, a sort of natural law, if we like. And I think this was one of the motivation for Milgrom to actually think outside the box and develop a theory in which the flatness of the rotation curve is an essential ingredient in order to understand gravity. So, so essentially the theory was developed largely in 1983, starting from this observational input that rotation curves becomes flat at large radii. But then starting from this input, one can use a mathematical model to make further predictions regarding the dynamics of galaxies. So one of the most important one is that actually this flat rotation velocity, which is a number that varies from galaxy to galaxy, is not a random number, but it correlates quite closely to the visible mass that we see. So essentially the mass that we are able to see and measure in gas and stars inside galaxies should dictate what is the flat rotation velocity that we can also observe in the other parts. And it turns out that actually this prediction has been confirmed later on during the years. So this was one of the motivations that has pushed several people to look more closely into this theory and further test it using a number of different observations and observational tests. MOND has been mostly supported by observations of galaxies and internal dynamics of galaxies, and this is the regime in which the theory is, let's say, doing well and is sane. The theory has been struggling more on larger scale, so-called cosmological scales, and one of the reasons has been that for a long time we had a theory that can be applied in the so-called non-relativistic regime, which means when the typical velocities are much smaller than the speed of light, and so this is also the regime in which we typically apply the Newton theory. But it has been difficult for many years to actually work out a mathematical description of MOND that also apply in the relativistic theory, so in the realm of the general relativity from Einstein. And it is not impossible though. In fact, over the past 20 years or so, there has been several attempts to have a relativistic version of MOND that in principle can also be applied to different problems, such as problem in cosmology, so on much larger scales than the scales of galaxies. And in particular, a few years ago, there was a theory proposal that for the first time has been able to explain the so-called cosmic microwave background, which is essentially the echo of the Big Bang to some extent, is the relic radiation from the Big Bang and also the oldest radiation that we can ever observe with our telescope. So that's sort of cornerstone for cosmology. And for a long time it was thought that the lambda CDM theory was the only model that could possibly explain in detail this cosmic microwave background. And a few years ago there has been a MOND-like theory from Skordis and Zlosnik, which actually shown that also in that context it's possible to explain the CMB. So this is one of the most recent developments that I think may further boost investigation in this context.
I am Elena Asensio. I'm a PhD student at the University of Bonn, working under the supervision of Professor Pablo Culpa. My PhD project is about understanding how the local group, this is the Milky Way and Andromeda, and other satellite galaxies and dwarf galaxies, how this group came to be in the context of MOND instead of the standard model. And well, there are many tests that one can do because there are many differences of what happens on the standard model and what happens on MOND. In MOND, you have that structures form from the collapse of big clouds, while in the standard model, you would have that structures form by smaller structures accreting bigger structures and then forming like the larger structures. And yeah, I'm trying to see if with this gas cloud collapse model, it's actually possible to form the Milky Way and Andromeda, because no one has really tested this, and I'm very interested to see if this is even possible. I honestly don't know if it's possible, but I guess I'll find out at some point.
MOND is a rather radical idea, because the main assumption is that the laws of Newton and Einstein has to break down at some scale, and in particular at low acceleration scales. So I think to some extent it's natural that when you propose such a radical and drastic idea, only a few people are open-minded to accept it and start working on it. So I think that from a more, if you like, sociological point of view, is not unexpected that the number of people working on MOND is much smaller than the people working in the standard context, in which one assumes that gravity works as we think it works, following Newton and Einstein, and we are dark matter particles. So I think in the end, things may change slowly with time as we further accumulate more data in support for one theory or another, and also when we further develop the MOND theory itself, because it's not, let's say, a full developed theory from a mathematical point of view, in the sense there has been several ideas, and there are several versions of the theory that are mathematically self-consistent, let's say in the non-relativistic regime, but as one goes to the relativistic regime, the theories becomes more complicated, and the developments has been quite recent, so let's say over the past 10 years or so. So it also, takes time for people to digest and assimilate these new type of theories. So I think it's a process that is naturally slow, and is part just of the way that science works, right? That to get to what possibly is the final theory will not just happen in one day, but it will take decades. So I'm quite optimistic that we will be able to test MOND further, both in different types of systems and also as a function of the universe lifetime, so back in time essentially. And I think this may give us further clues on whether MOND is correct or not. So my perspective at the moment is that MOND is a serious theory that deserves to be tested. It may be right or may be wrong, but for sure it's important that we go out and test it, because it is a serious scientific theory that deserves the attention of observers and theorists. I always try to be open-minded in problems, so I'm not working exclusively on MOND or exclusively on dark matter, but I have an approach that is more empirically oriented, and so I try to make the best possible observations and calculations in order to test whatever theory is on the table. And what struck me for now 10 years is that every time I test MOND, it actually works, at least on the scales that I'm studying, so the scales of galaxies and small galaxy groups. So I appreciate that many people that do not go through this type of exercise may not appreciate how closely MOND can explain the data, essentially as well as dark matter, but with less free parameters, so with less knobs that one can turn in order to explain the data. So I would say, I don't want to have a personal preference, but I would like the data to indicate what is the best route to follow.
If you are interested in learning more about Milgramian dynamics and the problems of the standard model, there is a very nice blog that is run by my supervisor, Pavel Krupa, and this blog is called The Dark Matter Crisis. And I think that this blog is very good at explaining in a not technical scientific way, but in a more simple way, what are the problems of the standard model and how does MOND perform in this kind of situations. So if you're interested in the topic, I think this is a very good blog to start with.
And that's it, I guess.